I'm May, and I'm a PhD student at the University of North Carolina at Chapel Hill. And right now, if you haven't put your email, go to this link. It's a little cheat sheet of the workshop. And there's a list of emails, and you want to make sure your email is on that list. You'll get an email to that email address. It might be in your spam folder. Make sure you have a Skynet account made. We're going to need it, and we're going to kind of do things a bit out of order. Oh, do you need the link still?
Link is in the Slack workspace. On the channel.
No, the mic. All right, does everybody have this link? It's in the Slack if you don't. And I'm going to do a little bit of talking while you make your account. So feel free to listen as much as you can while multitasking, but focus on the account. So this workshop is about some of the work we've done in our new course. It's called Astrophotography of the Multi-Wavelength Universe, or MWU, because the whole thing is a mouthful. And so what I'm focusing on is one of the first things we had the students do in the course. So brand new to the semester, we started out with things closest to us, the moon and the planets. And if you're just now coming in, there's a link in the Slack, a tiny URL. You want to go to that. It gives you a cheat sheet for the workshop. And there's a list of emails. Add yours to the bottom. We're going to make you a Skynet account. So you'll get an email, and it might be in your spam folder. But just follow the prompts, make your account, and that'll get you all set up. Awesome, thank you. All right, so like I said, we started the students off with all of the stuff closest to us, things in the solar system, things they were familiar with. And while you're registering for your Skynet account, I'm going to tell you a little bit about our network and what exactly you just made an account for. And we'll start going over a couple things. And then we'll kind of take a break once everybody has an account and do stuff in the way that saves us the most time. So again, this is that link. And it's also in the Slack along with the rest of the links. And these are those links. We have our students share. So the extras down there are where our students have shared some of their blog posts, which I'll talk more about in a little bit. But for the meantime, what is Skynet? And feel free to just yell if you have any questions. If you have trouble, we have people who know how to make a Skynet account here to help you. But what is Skynet? Skynet is a network of fully robotic telescopes spanning 4 continents and 5 countries. And if you're not familiar, what we mean by robotic is that there's no one there making sure the telescopes are taking the right observation. No one's sitting in the dome, making everything run smoothly. They run smoothly on their own with us safely in our beds at night and not having to stay up late. So we have about 20 telescopes. Some of them are kind of all ours, and some of them are with partner institutions where we took existing observatories and we made it so that they could be on Skynet. They're roughly 0.4 meters or 16 inches up to a meter. They're optical telescopes. We have one radio telescope that we'll use in a little bit, and we have a couple more that are being integrated to the network. But the nice thing about Skynet is that professionals and students both get to use it. And we have this curriculum, some you'll hear about in the workshops tomorrow. And then we have the rest also we use in our curriculum. The idea is that they get to use professional instrumentation and the same kind of instruments that you can do cutting edge research with, even if they're not doing that research. So I mentioned some telescopes that are all ours. Those are the prompt telescopes, and they are in Australia, Chile, and Canada. And that gives us some full sky coverage, both hemispheres. And you see data published in peer-reviewed journals about once every 20 days using data taken on Skynet telescopes. We have a few Nature or Science publications, and that's just the research side. But we have curriculum that's implemented by students around the globe, and it serves tens of thousands of those. And there's a couple programs. This curriculum is the result of one of them. And this curriculum is MWU. It's funded by a $3 million DoD grant for education. And if you're an educator, there are educator opportunities for developing the curriculum, which we're halfway through, and for implementing it and letting us give your students surveys so that our education research team can see how this curriculum changes things like attitudes and self-efficacy. And it's called multi-wavelength because we're looking at more than just the visible light. We have our radio telescope, so we make a lot of use of that. But we also have archival data from Spitzer, Weiss, Chandra X-ray data. So we're bringing in a lot of different things to help students understand what exactly is happening. But in the fun sense, MWU is astrophotography to do science. And basically, we're using these telescopes, we're getting really pretty pictures to study the solar system, stars and star stuff, and then galaxies. And we're going to focus on just that first bit. So does everybody have a Skynet account? All right. So we're going to take a little break here, and there's a link in the Slack, afterglow.skynet.unc.edu. So if everyone can go to that link, you'll log in with your Skynet account and you'll see something like this. And Afterglow you can think of as all-in-one image processing software. So you can do all of the technical things like aligning images, making a WCS, stacking them, and you can do photometry, all of that good stuff, but you can also mess with the display in kind of more like a Photoshop sense of the word. So once you log in, we want to open up some files. They're kind of big files, so we're going to get started on it now. This folder up here in the top left will open the files, and you should see something that looks like this. And you'll want to go to sample, and the path is in the cheat sheet too. But you go to sample and workshop. And then we're going to go to moon-align. This one right here. And you should see 27 images in there. And if you click on this button at the top, it'll select all of them. If I'm going too fast, just say hey. But select all of these images and click open, and you'll see the progress bar at the bottom. These are 5K by 5K images, every single one of them. So once we all start opening them, I just want to make sure we have enough time. But once you have those opening, you can just leave it for now. And we're going to use those in a bit. We did a little bit of the background work just so that it's easier for all of us, but you'll get to make your own at home too. We'll set you up for that. All right. So MWU, I already mentioned, it's astrophotography to do science. And here's an example of what Dan, back there in the blue, made when we were testing and trying out all of these things before we did them. And this is the Crab Nebula. And so just our prompt data is this over here. I'm sorry to zoom, it's the one on your left. I'm gonna be a disembodied voice for a minute. And then you can start adding in, you can start refining things, you can add in archival data. And the more you add in, the more of a complete picture we're seeing. So this is with infrared data. So we're seeing that gas and dust that's been blown off by the supernova. And this includes the Chandra X-ray data. So we can talk about the pulsar that's at the center and things like that. So we can start to have the students see in ways that are a little bit more intuitive, these things that we can't see with just the data from the telescopes. So some of our student work, as I said, it's published on a blog that is danreichart.com/mbob, and we've been featuring collections of what they've done because we want them to be able to share it and be excited about it because it's pretty, it's astrophotography, it's so cool. And we want to use that excitement to get them to talk about it and relay it in terms that anyone can understand. This isn't supposed to be technical writing, it's fun, it's enthusiastic, it's something you'd see in like a NASA article where they're talking about like an APOD. So this is a collection of what our students did, and now we're going to do the same things. But you can check out their blogs. We're pretty proud of them. And this is again just the links. But we're going to first make a lunar mosaic. Our telescopes, we're using one with a 15 by 15 arc minute field of view. That's smaller than the moon. So we need to do a 3 by 3 grid to put that all together into one picture. And we're going to use the data that we're opening up right now, but I'm also going to teach you how to put this in on your own. So this is where your cheat sheet is helpful. So now go to the skynet.unc.edu link in the Slack. I know it's a little bit all over the place, but sitting and waiting is much less fun for us. All right. So if you're logged in, this is Skynet. And what we're going to do is submit an observation for the moon tonight. So you'll hover over the My Observatory and you can click optical observing. And you should have nothing here, but I have quite a bit. And we want to add a new observation. So then we can put in the moon and it will find the coordinates of the moon. It'll update it so you don't have to worry like, oh, the moon moves fast. It's okay. You can just use the keyword. There's some things that are set by default that aren't helpful. So if your min-moon separation says 30, we want to change that to 0 because we can't avoid the moon and look at it at the same time. And everything else you can leave as is. If your max sun elevation says -18, you can put it to -12. The moon is plenty bright. And this is where we get into the little nuance of the mosaic. In this advanced settings tab, you want to enable dithering, this little checkbox right here. And then go to the cheat sheet. And in our optical observations of the moon, there's a table right here. And so there's a couple different telescopes. I don't recommend the NSO one because that's not a mosaic. So where's the fun in that? But the prompt telescopes are all in really, really dark skies in the southern hemisphere. So prompt 6, if you want to use that, it's a 15 degree or 15 arc minute field of view. And prompt 5 and prompt MO1 are about 10 arc minutes. So if you want to use one of those, then you'll want to do a 5 by 5 grid. It's up to you here, whichever one is really speaking to you. I'm going to put mine in for prompt 5. So I'm going to change this to a 5 by 5 grid. And the cheat sheet tells us that for prompt 5, I want 390 arc second spacing. that gives us a good amount of overlap, so we can still align the images right. But we can still get the whole moon. Right. And you can ignore everything else. This is neat at the bottom. It shows you when your target is observable. So if you chose prompt MO1, that's Australia. So it's observable right now. And it'll only show you for both when it's dark, and then that line shows you when it's high enough up to observe. But we'll choose our telescope. And now whatever telescope you picked in that list, make sure you pick that same one now. You might not see as many telescopes as I have here, but I'm going to pick prompt 5. Make sure you just select the one you picked. And we'll save and continue. So this is our filters page. Since the moon is really bright, we're going to use narrowband filters so that we can take a little bit longer exposure and get away with it. So you'll want the U, H alpha, and O3 filters. Not all of our telescopes necessarily have these filters, but just any telescope you have access to, it has some of the filters in this list. All right, so now we can add our exposures in, and make sure this doesn't say this generic telescope. You want to pick whichever telescope. So I'm using prompt 5. And for our exposures, you're making a grid, right? Either a 3x3 or a 5x5. So you need some multiple of that number. For any of the 5x5 grids, you're going to want 25 exposures in each filter. And for the 3x3, you'll need 9. So there's also a little table in the cheat sheet that says how long your exposure time should be. This one right here. All right, everybody's doing okay? All right. So now you should only have one option here, but you'll just want to make sure your time account is selected. That's how we charge you. And I'm just going to pick this one. And you'll want to do the sequential filters. So it takes all of one filter first, and then it'll go back and do the other filters. So make sure that's checked. And everything else you can leave alone. Save and continue, it'll take you to the checkout page. And so again, if you're doing a 5x5, make sure you have some multiple of 5 in your exposures. Make sure the time you put in hasn't changed. And then we can just submit. And now it'll show up that it's active. So it's ready as soon as the moon is up and observable. And if there's good weather, it'll start taking your images, and then you can actually see as they come back, they'll all appear here. Does that make sense? Everybody doing good? All right. So now we can go back to the Afterglow workbench, that afterglow.skynet.unc.edu. And we should all have 27 pictures in here. And if you zoom out, you might be zoomed in. You notice they are big. They're going to take a second to load. But basically, what we've done is we've put in an observation, so it'll get a grid like this of pictures of the moon. And what I've done behind the scenes is I've already done the alignment bit. So we have this neat features alignment where it's matching features between images to try and find which images should be next to each other. We don't have stars, we can't really make a good WCS, so we're doing this instead to get really good alignment. And so I save time because there's a lot of features on the moon. It can be a bit long. So I've already done this for us. So each picture basically looks like this right now. And what we're going to do is we're going to put them together until we get 3 pictures like this. And then we'll just combine them. And then we can adjust them and we'll have a full color picture of the moon. All right. So over here on the right, these are all of our tools. And we're going to, when you're doing this on your own, I'll have more updated instructions in the cheat sheet for after the workshop. But if you were taking your observations that we just put in, you'd want to go to the aligner tab first. And this is where we make those big images and get everything in the right place. And you'd enable the mosaic mode and you'd use features. And I'll put this all in the worksheet, but this is just an idea of what it's doing. This is how it matches things, and there's some adjustment here. If you put prompt 5 in for your observation, you might need to adjust this ratio threshold. It happens. Sometimes you just gotta play with it until you find the right thing. But I already did this, so we can go straight to stacker, which is the second from the bottom. And here you're gonna wanna make sure you only stack the images in the same filter. So you can filter it really easy by going to the left and typing in H alpha. And now if you look in this drop-down menu, it's only your H alpha images. So we can select all of those. And we won't worry about any of this stuff right here, but you want to make sure this equalization is on. Multiplicative, additive, and global. And what that's doing is basically adding some kind of correction factor to treat the images. It smooths out the seams where they overlap. If you didn't choose prompt 6 in the images you picked, this should be 0. But since we're using prompt 6 here, we're going to use 1. It just smooths it out a little bit better. And then you can start submitting. And we'll rinse and repeat with our other 2 filters. You can keep all the settings the same, just change the images you're using. And you can set them all to go while the other one's still processing. Everything is done through the web browser, so it's all on the server. It's not on your local machine. So you can close the window and reopen it, and it'll still do what you asked it to. And be patient, it might take a second, especially when all of us are doing it at the same time. This is why we didn't bother aligning it. It would use up a good amount of time. So a couple little things just to know when you're doing yours, you'll get yours back and they'll actually all live instead of where we found them. If you go to Skynet Robotic Telescope Network and user observations, then you'll find your picture of the moon here. It'll be in some kind of folder with your telescope, and you can just open up this folder and bring in all of your images that way. You'll want to use the reduced ones. They're already corrected. Don't need to worry about your bias darks and flats with that. So you'll just open up all of the reduced data, and then you can do the same process. And so what we're doing is we'll keep all of these original files right here in this is our workspace right here, the little area. And what it does is it makes a new image for each filter that's that filter stacked. And that's your completed image. So this is going to be our red image right here. So we can already see that it's come together nicely. It looks nice and aligned. Nothing's in a place it shouldn't be. You can kind of see here where these seams are. That's just a product of the alignment, but they will come out easily once we actually start the color processing. So once you have all three of those, you want to right click on your stack images. So this is my H alpha, so it'll become our red. And you go down to color map, and I'm going to map this one red. Our O3 is going to be our green. And then our U is going to be our blue. If you don't like having all of these in your little workspace, you can get rid of everything except the stacks if you want. But I'm just going to keep them all. All right, so now we have, does everybody doing good? Great. So now we have our three individual colors. So if you select just the stack images, nothing else, just the stack. Then where these three dots are, you can group the selected files. And this is what makes your actual color picture. So now all of those are in this new file where they're just individual layers that we can adjust. And there we go. So there's our color picture of the moon. It looks mostly gray. Our students were also like, this is gray. But you can start to already see the subtle differences in color. This part is more bluish gray. This is more like a dull gray over here. And we can bring that out even more. We can do some adjustment here. And then I like to also just export the picture at the end of it and use my like Mac photo viewer, preview Windows photo viewer, whatever you have, to kind of bring out the sharpness and the contrast a little bit, just because it is very subtle. But if you're on this file, the moon dash something.bits, that's your group layer. And so if you're selected on that, go over to the right side and you want to show display. It's the very top button. And there's lots of all sorts of advanced stuff here. If you come to the talk on Friday about the star forming regions, you'll do some more of that advanced stuff. But this is really simple. So we have our, first we want to change this to our H alpha up here on the top. So now we're looking at the group layer so we can see how what we do affects the group. But we can make the adjustments just to the red layer. And we're going to go to color composite tools and link all layers in percentile mode. All right. For the blend mode, I like the lighten blend mode a little bit better. You can use screen, I just like lighten. And then down here, we want to go from linear, which still looks good, to mid-tone, which helps us get rid of some of that stuff in the background a little bit easier, I think. So you're in mid-tone and your image looks like that, which is not what we want. So press default preset and it will adjust itself. Give it a second. There, so that looks better. It's a little dark, it's a little dull looking, but what we can do is a couple things. We can raise the background level to say like 10, 20, play around with it, it's up to you. This is where we get into just the aesthetic of what you like best. So if we raise the background level, you'll notice that those seams in the upper corner start to go away. And that's because we're just bringing up the threshold of what is black, what is zero counts. And then we can also bring down this mid-tone level. And by doing this, you're kind of saying we're lowering where the middle of the data is. We want to be careful. We can also mess with the saturation level, but we do want to be careful because this is still pretty bright. We can overexpose and saturate some of these spots down here really easily. but you might have to give it a second, but go ahead, you can adjust to your heart's content. If you wanted, you can even change the color map to something fun and different. If you want to make some kind of crazy moon. All right. So then once you're done, and you can adjust it all you want. Feel free to keep adjusting it while I talk. But for me, this is fine. This is good. So I'm going to down here, export as a JPEG, this little typical picture icon right here in the middle. And I'm going to open it and adjust it just in my photo viewer. So I can bring out a little bit more sharpness. I'm going to kind of raise the contrast a little bit, turn up the saturation. When we were doing this in class, we were advising the students that you can end up oversaturated and with a less than real look to the moon, but it's all kind of up to the aesthetic. So I'm just gonna mess around with it. I'm gonna kind of oversaturate mine so that I can make a point and maybe it's easier to see, especially on Zoom. But this is pretty neat. We ended up with an actual color picture and the moon mostly looks gray, yes, but you can see the differences here. So this was a good opportunity to talk about what these colors are, especially the more subtle things that you might not be able to see with the naked eye. So we can see the bluish areas and we can go into a discussion about how those are titanium rich basalts. And there's some more reddish areas and those have iron in them. In this, you can see wood spot, which is down here towards the bottom. And we can talk about the glassy deposit. So we can use this picture of the moon to talk about what makes it up, which is pretty neat. And this is just with like a couple seconds of data. This is nothing. You have 15 minutes worth of time. And so you used like a minute and a half or something on this. So you have plenty of time to take more. Try it out because you can do this with other things too. And you can do it without the mosaic and just take the same picture to try and get better signal to noise, all that kind of stuff. So feel free to go wild with your 15 minutes. All right. So that's our moon mosaic. And the next thing we did, which this was exciting, everybody knows the moon, everybody loves the moon. The next thing we did was bring in some radio, which if you weren't at this morning's workshop, the idea is that we can look at both of them and they tell different pictures but the same thing, and we can get a really cool idea because this is our reflected sunlight. And in the radio, we're not seeing that reflected sunlight, we're seeing this thermally re-emitted light. And so we can use the radio observations to get the temperature of the moon, which we'll do in a second. But first, we have a 20-meter single dish radio telescope at Green Bank Observatory in West Virginia. And when you take an image, this one, the one we'll do, uses a raster pattern like this, where the telescope sweeps back and forth and takes pictures as it goes. Instead of stopping and starting, it's just gonna move its whole dish around and take pictures on the fly. And you get this spectra, which is cool to us astronomers, but less cool to intro students. And so we can take that, use this really sophisticated algorithm that's in Skynet, and remove the noise and make an image out of it. And then we can actually do stuff with that. So this is just kind of the intro, because now we're going to put in another observation. I'm going to use a little bit more of your time that we gave you. And so now go back to Skynet. And instead of the optical observing, we're going to go down the next tab is radio observing. You also probably have nothing here. That's okay. And it's really similar. Add a new observation. We'll look up the moon. And you can use this viewer to see when the moon will be up. Our radio observations will all be at Green Bank because it's our only current radio telescope. But you can go by hour to see when the moon will come up and when your observation might be taken. And so here, there's the same kind of visibility chart. We don't have to worry about the moon separation because this is the radio. If the moon was up right now, we can just start taking, pictures. But we're just gonna save and continue, and we're gonna use low resolution mode. We're using the L-band receiver. And so we've got that, the 21 centimeter cold hydrogen line. That's just the area we're looking. We do a lot more with it in the whole course. But right now, we're just using it so we can get our spectra, basically. All right. And you'll pick your time account. For you, that should be very easy. And what we're going to do is a map. And that map is going to be that back and forth sweeping pattern. And we're going to choose by beam width because this is basically a 1 pixel camera. So we're just going to set how big of a picture we want by how many sweeps we want it to do. So we'll do, you can just put in 6 by 6. And it'll automatically make that into degrees, but we just want 6 beam widths by 6 beam widths. We'll have it sweep in RA, so it's sweeping horizontally. And this is all in your cheat sheet too. It's the radio observation. So all that info is right here. But you can go back. So if I'm going too fast, don't worry, it's all there. And we're going to look at the, we're going to do a physics beam. And sometimes it helps, it's not a huge deal with this. Sometimes it helps though to increase that integration time to a half a second, just because what's happening is the telescope gets swinging kind of fast. And we can save and continue, and we'll just confirm everything looks good. We'll submit our observation. And now it's ready. The other thing with the radio is that when we get this back and we use this algorithm and we have this image and we try to do something with it, it's going to be in pretty arbitrary units. So what you want to do is get a calibration source. We have Virgo coming up, Virgo A. So we're going to make another observation, but this time we're going to do Virgo A instead. And we're doing this because we know the actual brightness of Virgo A. So we can use that to help go from these arbitrary units to something physical. So you can just do the same exact thing. A lot of your settings here and everything will save. Still make sure you're doing low res mode. If you try to do something crazy, it'll use a lot more credits and you don't need it, just the moon. All right. So then once you submit another observation, if they were up, we could actually see it going right now on the Skynet page. There is this little Skynet live view. And so you can see all the telescopes that are online. You can see if they're working or if they have bad weather. Unfortunately, it looks like Chile has bad weather tonight. And you can see somebody's observation is being taken. This is our partner university or our partner observatory in Poland. But you could actually see if we were looking at something that was visible right now, it would take a little bit and then come in here and start taking our observations. All right, but because the moon is not visible, everybody good? You all have your calibration image submitted? Okay, cool. There's some background work that is, there's a link in the cheat sheet that gives you all the information about what to do when you get that back, if you want to try it. But we're just going to use the stuff that's already done. So I'm going to clear out all of these because I don't like having a bunch of things in my workspace. So you can select them all and then close the files. And I'm just going to discard all the changes because I don't need them. All right, so now we can go back to open up the files. And you're probably still in the sample workshop. But this time we're going to do radio moon. And so there's two files in here. We took these earlier, so we used Cygnus A as a calibration source, but it's the same idea. So select both of these and you'll see something like this. Isn't that pretty? It looks just like the moon. So when you get this back, if you follow the guide and you do this on your own, then you'll actually have a file that has a bunch of different layers to it. We just picked out the important layer. It's the main layer. And what we want to do is we want to change a couple settings first. So we want to go to settings up here on the top. And then on the left is aperture photometry. And you probably have something like 5 and some small numbers in here. You want to change them so that your centroiding radius is 28 and your aperture is 28. Your inner annulus should be 50 and your outer should be 70. This picture is big, so the kind of photometry settings are defaulted for optical. That's not going to work in the radio, so we're going to just adjust it and make sure we have a big enough area to actually do some photometry. All right, then you can just click back on the workbench and that'll bring you back to this. And before we go any farther, in the cheat sheet, it's in radio calculations. There's what I just covered, but then there's an add your measurements here. So that'll take you to a Google Sheet. And we're going to do some photometry. We're going to get a value and we're going to put it in here because I did all of the tedious stuff to do the calculation. So once that's opened, go back to Afterglow. And on the right is this one, photometry, the little light bulb. All right, so make sure your settings are on because it's neat and you can see them. And we just want to click somewhere near the center. So whichever one you have open first, mine is Cygnus A first. And I can just click on it and it does the photometry for me, which is sweet. And it gives you a flux right here. And this is in those arbitrary units. And it changes based on the day. That's why we want our calibration to always be done when we submit the actual observation we want, because the receiver can be different. So you always want them to be close in time. So I'm going to take my number and I'm going to put it in here. So everyone feel free to add your names to the sheet, put in what numbers you get. And then you'll do the same thing with the moon. If something seems weird, if you don't have these giant rings on yours, just let us know. Yeah, so moon is the first one, Cygnus A is the second
Now, do you remember the tiny URL MWU
one, dash planets.
planets? Thanks.
All right, while you add those in, I did all of the calculations over here. And what we're gonna do is use our calibration source, Cygnus A, to get the flux density of the moon in Janskis. So then we can actually get the temperature with this awesome equation that's in here, right there. So our S in this equation is going to be our flux density. The distance I already put in because it's just the distance at whatever time you took the observation. Nu is our central frequency from our observation, so that's 1395 megahertz here, but I have all of that in, so you don't have to worry about it, it's just fun facts. When we did this in class, we had many unit problems, so people were getting like 10 to the 26th Kelvin, which is a bit warm for the moon. All right, so you can copy these cells. And if you go to where it says moon flux sig A for your column or your row, then you can paste special and paste the formula. Man, there's all of the tedious work done. So we get a temperature of like 244 Kelvin. It's a little cooler than like room temp for the temperature of the moon. When we did this, and if you wanted to, you have the time to be able to, you could take another observation a few days later. If you want to show yourself that it's actually just kind of relatively constant and it's not changing with phase. If it was changing with phase, we'd be looking at reflected light from the sun. So as the moon goes towards Nu, we'd see a colder temperature. Trust me, we did it. You can read about it in our students' post. But the temperature stays constant, which was pretty neat because we had the students trying to figure out, is it reflected? Is it some kind of other thing? What is this radio emission on the moon? And so it was a good lesson to teach them about how these different types of light work. I know that was like the super exciting part. So this just is all to give you an idea of these things we can do with even a little bit of time. And this also we can start doing as a team. We're not going to, but the students did. And it made a good kind of team building exercise, especially with the radio, because it was all something really different for them. If you want to read in detail about the algorithm that makes it possible, there's the citation for the 50-page paper. And I know you're still finishing up your moon stuff, but I'm really excited about this last one. And we're going to make some color images of the planets. What we did this term was we did Mars, Jupiter, Uranus, and Neptune, which is pretty neat. So they got to see a terrestrial planet. They got to see the red on Mars. It had just been at closest approach, so it was a great time to look at it. Here we have Jupiter and Uranus on the left and Neptune on the right. And you can even get enough color out of them to tell that Uranus is a little bit more greenish blue and Neptune's more of that true blue. And what we ended up being able to do was have the students talk about the composition. So the different ice clouds in Jupiter's atmosphere, the methane ice, and how Uranus's atmosphere is kind of hazy. And so it makes it look more greenish. And we're not going to submit an observation for this one. Saturn is rising in the morning, so if you want to, you can submit an observation. There's a link in the cheat sheet that tells you some recommended exposure times. But we're just going to do Jupiter. I know we're going back and forth a lot. But go back to Afterglow. You can clear out your radio stuff because we don't need it anymore. And this time, we're going to go back to workshop and we're going to do Jupiter color. When we actually had the students do it, Jupiter was setting, but these were taken when Jupiter was not setting. So we got it when it was higher up, and so the image looks better. You might want to take off the photometry tab. You can just ignore it. We're not going to do that. So again, Jupiter is really bright. We used H alpha, O3, and U as our proxy for our red, green, blue filters, just so we can get a little bit longer exposures.
I just looked up and it was an orange.
Here we go.
Yep.
Oh.
1 sec.
It really is just like class all over
I
again.
don't even know that it matters though. There's lots of things. Now it matters.
All right, trying it again.
Thank you earlier. Okay. All right, good thing there's more than one. So that's all right. All right, so pick a TV to look at, but so this is what we have at the end of it. You can see all 4 Galilean moons in this one. We can actually, when we're done, adjust the colors and make Jupiter oversaturated and pull out some colors on the moon. But first, we're gonna actually deal with these things. So what we need to do is make sure they're all really well aligned. And again, we don't have a WCS here. There's no background stars. So instead, we're going to use this fancy algorithm that we have to just click the center of the planet and it will do the alignment for us. So we're going to go to source catalog, which is the little star on the right. You should have nothing in here like that. So make sure your planet centroiding is on. I like to unclick the include sources from other files while I'm doing it. If you read the whole guide and try to do a picture of like Saturn later, you'll see that you have to click in every single image you take. So when you have like 30 images, it gets to be a lot of marks. And so now we can just zoom in. One thing you might want to do first, mine is already this way, but it is these workbench settings over here on the left. So zoom in whatever your top image is to be your H alpha. And then go to workbench settings. And sync your orientations and make sure that it's on pixel. And then make sure the sync display settings is on. This just makes it easier. You don't have to like move your images around. They all zoom the same way now if you switch between them, which is pretty neat. So now we can go back to our files and you just want to try and click as close to the center as you can. It will get it pretty well with Saturn. With the rings, it's a little bit more finicky, but especially with Jupiter, it's pretty good about it. So just click somewhere near the center and just click once so you'll see your marker. If you have more than one in here, delete the other ones. If you accidentally click twice. And then we can switch, and we want to do that for every single image. And once you're done, if you turn the include sources from other files back on, you'll see all 3. So now we want to select every one of them, and we're going to merge them together so that it starts to recognize that it's all the same thing. And you want your images are not aligned or registered, and then you can leave the number as your label, but I like to say what planet it is. So I'm going to call it Jupiter, and I'm going to merge the sources. If you get an error here, make sure you don't have more than one click for each filter. All right, so once that's merged, we can go back to the aligner tab. And you'll want to make sure your mosaic mode is off if you've turned it on like I did. And we're going to select all three of our pictures. And I'm going to choose H alpha as the reference. It doesn't really matter. But instead of whatever mode you have here, we're going to do sources manual. And so this is going to take those sources, we just told Afterglow where the center of Jupiter is. It's going to take those and align those for us. And down at the bottom, make sure you click the right thing. If you wanted to do a bunch of different planets, you could have them all in and do all of the clicking, but then you have to sort them. You have to sort them out. So make sure it knows what you're trying to align, and then you can submit the job. And it goes pretty quick, especially with just these three. All right, so everybody doing good so far? No errors popping up? Awesome. So now we're going to do the same thing we did with the moon, and we're going to color each of these. So U is blue, O3 is green, and H alpha is red. And then you can select the files and group them to make our one color image. So I have something like this, and you can kind of already start to see the colors in the moons. Jupiter is really overexposed, but you can kind of already start to see that the moons have a little bit of color to them. But now we can go up to the display options again. And I like to be on the group layer over here and the H alpha layer over here. And we'll go to color composite tools, and we want to link all of the layers. We're just going to link them all to red, or to H alpha in this case, so that we adjust all of them at the same time. And I like to go to midtone. And then it's the default preset. But Jupiter still looks really overexposed, but if we hit the right target button, now that looks a lot better. The moons are gone because we've turned the saturation level way up to try and not oversaturate Jupiter. But now we can start messing around with the settings a little bit. Zoom in a little bit more. And you can see we got the great red spot in this one, which is pretty neat. So I'm going to turn, especially with Jupiter, it's very bright. So I tend to not mess with the saturation percentage, but just this midtone level. And you can see as you do, it brightens it up. So you can start to see the edges. And it's a balancing act. Once you move it down too much, you're going to lose some of that definition in the brown cloud belts. But this is all just a taste. Doesn't have to be what I put it at. Just whatever you like best. And if you wanted to, you could really bring the midtone level down. And once you can see the moons again, you can start to see colors. This might be a little bit too far down even for that. So here it is. And we can start to see more colors in the moon here. You can see this one looks more yellowy and the others look more white. So the yellowy moon of Jupiter is Io. And so we can talk about how it's volcanic and it's more yellow, where the other ones are icy. And so they're white. And if you really play around with it, you can even start to see that one looks a little bit more brighter white. And especially in the images our students took, they'll talk about it, how you can tell which moon is which because it's bright or white. So it's Europa, 'cause it's like bright, clean, white ice. But I'm gonna put this back to how I had it. And then you can do the same thing. You can export it as a JPEG using that button on the bottom. Once you have something you like, you can adjust it in your photo viewer if you want, but there's a really cool picture of Jupiter. Some of our students did such a good job that I actually thought they had copied it from the internet because it looked so clear and so crisp once they were done. So. Yes.
When you use this in your classes, how much of it is kind of guided and how much of it do students get creative license? Like, has there been a success rate in them generating their own research questions that they're kind of using Skynet to study, or do you say like, this is the curated plan that you're going to follow?
In this course, it's more of a plan, especially this is the first thing we do. So we're really introducing them to all the tools. Just like this, we have to introduce them, teach them how to use Afterglow and Skynet. Once we get further along, so we start looking at star clusters and star forming regions, and we have each group pick a different one. And so then you start to see the subtleties come out. So like when we were doing our star forming region, and the students were like fighting each other for the one they wanted. They were really into picking their star forming region they wanted. A group had one and they were super happy with their image, and it comes time to do the physics, which you'll hear about on Friday if you attend that workshop. And this group was like, I don't have anything. I can't, there's no star. We needed the star driving the region and I can't find it. And so we start looking on the internet and trying to find what it is that's driving this region. And what they had picked was a small part of a star forming region. And that part was mostly a reflection nebula. So it was reflecting light from the star that's in a different part, that's farther away. And so then we got to talk about, well, how do we see that in your image? And so they got to start questioning things and find out the answers to those specific questions based on their object that it chose. And so a lot of good things came out of that. We got to talk about pulsars, and they got to start asking, like, what are the harmonics? Like, what are these things, these other things that I thought were the period that aren't? So there's a lot more once they branch off to the more advanced modules in the course, but it's overall pretty curated. But there's a lot of room for asking questions and really expressing the things they liked most or the questions they still have in the blog style post that we have to do. So if you want to know more, if you're interested in being on the development team, we have a 1.5 years of development left. You can email me, you can email Dan in the blue. And there's also more information on this tiny URL right there. So if you have questions, feel free to hang around, feel free to talk to us. Otherwise, you're out a little bit early. Yeah, so feel free to wander, feel free to mess around with your images, ask questions, whatever you want to do. Yeah. We have students outside the university level. We already have some high schoolers that are implementing parts of it. One thing with this is that you can take pieces of it. You don't have to do the whole thing like we did. The surveys and the education research part of it, that's for university students. But you can still implement it with your high school students. We have somebody that already has, and they'll be speaking Friday to let us talk. So our speaker on Friday is one of the people who's already starting to do this stuff with high school. As much as we can, we have them use their own data. If you implement the course, it comes with telescope time for students. And that is for them to take their own data as much as possible, because that data ownership and like, I made this myself, I took this observation, I made it, I did everything to it, was really exciting for the students. So we wanted to get that as much as possible. If we have only like one planet visible, then we're gonna pull in some of this old data so that they can still see more of the planets, but as much as possible, we want them to start with their own data and then use archival data to enhance what they already have.
So if they get their data, they have one range from all the corrections. Doesn't have that.
Skynet will automatically return your biased, dark, flat, corrected images, so those are already there. It's just sometimes you might need to remake your WCS or you need to align the images, and that's all walked through in the guides. And that's kind of shown to them, so they become pros at it. Once we got a couple of like modules in, they were coming to class with that stuff already prepared, so we could just do the fun stuff in class.
There's also, base in the. Did the state of the public knows what they're going to have to do the last time. How much states in the class? In the, maybe you could buy it.
In some of the later modules, and we'll see this 2 days from now, Matt's talk. We supplement with spitzer data, for example. Like star forming regions, you can get a lot of half galaxies as well. If you bring in the warm dust, long with physics, and that stuff you don't have to out there. You can just load it in and align it, prop it, incorporate it.
Hey, since we have a few minutes before, like, speaking of data, we'll have to, so that we can take, this, Saturn. Would you walk people through
Yeah.
setting up an observation on Saturn?
Yeah, if anyone wants to take an observation of Saturn, I recommend in this cheat sheet going to the module 1C guide. Oh, that link's the wrong one. Just 1 second. A little bit tired when I linked these, so I linked the wrong one.
We're also going to do a Saturn observation. You come to the OBIS workshop tomorrow. It's the introductory curriculum. This one is more advanced curriculum, and we'll walk through a Saturn observation as well.
So I'll just actually put it up here, but I'll also link it in the cheat sheet. So this gives us an idea of what we want for exposure times for all of the planets. So you can keep this in your back pocket, and as the planets are up and visible, you can take more observations until you run out of time. But we can go back to Skynet and to your optical observing. And the same as before, we add a new observation of Saturn. And you can leave everything else the same. We can see that it'll be visible in a little bit here if the weather was good in Chile. For the telescopes with things like the planets, it's best to use the smaller field of view because they're already small. So prompt 5 is a good one. And then for Saturn, so it's divided between the planets. For the really, really bright ones, we want to use the narrow bands, but for Saturn, Uranus, and Neptune, we can use a classic DVR filter. So instead of using your narrow bands this time, you'll want these 3. And it said for Saturn, you want to do 30 exposures in each filter. That helps bring out a lot of detail. You could do it with less. If you do it with 30 exposures in each filter, or wait, no, this one is.
Yeah, Saturn's 30, but that's if you want to bring out minor emergence. You can get away with just 1 if you just want to look at the minor.
Yeah, so you can do less. If you do 30 of each filter, you have to click through 90 images to align it. So I'm gonna just do 10. And here we have different exposure times for each filter. So make sure to check the little chart, but it's 0.3 seconds for B, 0.15 for B, and 0.075 for R. Also, if you are interested in doing something that takes a little bit more time, if you do less exposures on Saturn, you get to do more observations. And again, make sure you don't have the generic selected, make sure you have actual prompt 5. And this, you could do the interleaved filters if you wanted, so that if some of the data comes back bad or something, then you still have a good amount. So if you switch it to the interleave, it'll switch between filters and then take the observation over again. And with this, it also helps because if somebody else took like a really bright picture of Saturn first and they just like really overexposed it, or if there's some other weird artifact in the images, you can delay it and repeat the observation, but we'll just take them. And then you can just submit. And you'll see an image, your images of Saturn come back once the weather clears up in Chile. There's like 300 and some clear nights a year, but all of the bad time is in their winter, which we're in. So sometimes it takes a couple days. Then you can, spend tonight after the reception, checking on your images. This is what everybody wants to do. And that is just sit up and watch their images. It's no different than taking them at that point. But yeah, so thank you. If you have any other questions, you want to stick around and chat. Otherwise, thank you all for tonight. Were there any questions on slide? Okay, cool. All right.
Brought you.
Thank you.
You
I
are allergic to anything.
Nope. And I love cooking.
Oh, good.
And I love
Okay.
dessert.
Awesome.
We do the students, well, they give the students donuts on their last day of class for the final exam period, and then we send it to the last surveys.
Yeah.
And it was awesome because I could use my TA's seniority to take pictures for video.
There it
So I got
is.
2 good donuts.
There it is.
You'll be asked to approve a supply. That's where it should be, but